Okay, so after we set up the first two, we are now looking at this third problem here. And we are going to find ACM. So, okay, we're given this round object with a mass of m and this radius and a certain moment of mass moment of inertia, and we're rolling without slipping down a ramp, and we have this angle theta. So because we're rolling without slipping, we know that we have some static frictional force that's preventing the slip. So we drew that on our figure here. And we're trying to find the acceleration of its center of mass. So how fast is this point right here accelerating? Just this point as it's going down the slope. Okay, so to start, we're going to do a couple of things. First, we're going to pick our coordinate system. I'm going to choose this to be my coordinate system. Okay, so positive x down the slope and positive y. And I know that my center of mass is moving down the slope this way, right? I, however, need to solve for it in terms of these variables, m, r, theta, and g. So I'm going to have to relate my torque in this equation as well. So there are a couple of things that we're familiar with from our previous problems. Summing forces in the x and y direction for our dynamics problems, and we're finding them equal to the mass times some acceleration in x, which may or may not be 0. The mass times some acceleration in y, which may or may not be 0. But one more thing that we're going to do today is we're summing the torques, and the sum of the torques is going to be equal to the moment of inertia times some angular acceleration, okay? So as we saw in the intro, torque is kind of analogous to our sum of forces equations. This just basically gives us one more equation that we can use to solve the problem. Okay, so now, what we're going to do is we are going to do our free body diagram. So our steps here, we're going to do 1, our free body diagram, 2, sum of forces, and sum of torques, and then 3 is going to be algebra. Okay. We also have one more relationship that we can use for this problem. For rolling motion without slipping, so rolling motion without slipping, which is what we have here, so it's rolling in the slope and it's not slipping, we can relate the linear acceleration of the center of mass to the angular acceleration of the center of mass. And the way that we can relate it is we can use this equation. So the acceleration of the center of mass is equal to the radius times the angular acceleration. So angular acceleration moves around, right? Angular acceleration is how fast it's accelerating while it's spinning. And then this acceleration for the center of mass is if I have this point in the middle, the center of mass point, I want to figure out how quickly that point is accelerating. So how quickly just that point is moving. It won't be rotating with the system because the center of mass point will not rotate. Okay, it'll be a fixed point in a system if it's at the center of mass. Okay, so let's set up our equations and see what we have here. Oh, first let me do my free body diagram. So we have our frictional force on there. So we have our static friction, okay? Now let's see what else we have going on here. I have my weight going straight down, right? So my weight is equal to mg because they give us big M for our mass. I also have a normal force, which is acting here, right? And preventing the object from falling through. And I know that if I have something at a slant, the angle with my normal force is going to be theta, and that'll help me break up my weight later into x and y components. Okay, so there we go. Okay, so now we have everything on our figure, and we need to look at our number 1. So we did our free body diagram, so I'm going to just say check for that. And now we're going to look at our sum of forces and sum of torques, and then we're going to do some algebra. So sum of forces in the x direction, what do we have? Well, sum of forces in the x direction, we have, if I model this as my positive x, I have negative f of s, right? And then I have plus mg sine of theta for that weight. If it doesn't make sense to you with that angle, so it's not immediately obvious, so this is across from my theta. I still did see a lot of people who had trig issues on the exam, so if you're still struggling with that one, definitely review those. Okay, so, and then that is going to be equal to, right, m times ax. And in this case, my ax is going to be my ACM, right? ACM, because this is my center of mass, and because this is rolling down the slope, if there's any acceleration going down here, that's what my center of mass is experiencing. It's the fixed point while the object is rotating and it's moving down. Okay, sum of forces in the y direction. So what do I have for this one? Well, I have a normal force, right? Normal force. And then I have minus the wx piece. So this would, or the minus the wy piece, sorry. So this would be the direction that my wy would act along, right? The broken up weight. So if this is my weight, and I break it up along the y direction. So my wy is going to be equal to mg cosine of theta, okay? Because it's adjacent to that angle, it would be along this side. Okay, and I'm going to set that equal to may. And in this case, because there's no acceleration in the y direction, this is not moving up or down. This object is rolling on the slope, so it's not bumping up or down along this axis that we chose for our y. So it's going to be equal to 0. Okay, now let's look at the torques. Okay, so one very important thing about modeling objects that are rotating, normally when we've dealt with blocks in the past, we've modeled it as a point, right? We can model all of the forces acting on a particular point. For rotating objects, we can't model it as a point because the distance that the force is away from the radius is important to us when we're looking at the torques and how it affects the rotation. So the general equation for torque is the radius times some force times sine of theta. Okay, so what does that mean here? So when I need like some sort of a lever arm to produce torque. So if I have some force and this is my radius away, this would cause it to spin this way, right? One other thing about torque too is the counterclockwise direction is what's modeled as positive. So in this case, if we think about if we have a torque and we're pushing this way, this would be a negative torque, right? If I had a force and I was pushing the opposite way, this would be a positive torque, moving in the counterclockwise direction. Okay, so we know in a couple of cases we don't have a torque where if we have a force that's acting directly at the center, that's not going to cause any rotation, so we don't have a torque. And then also if I have a force and it's just acting like through along the direction of the radius, that also will not produce a torque, right? It's also not going to spin. Okay, so just some things to keep in mind. So let's think about that as we're looking at our figure and how we're going to model this. Okay, so if we look at our weight, it's acting through the center of mass. So my radius, it's not any distance away. I'll write out the equation for what it would look like. So it would be radius times, mg sine of theta. And I'm going to model them all as positive right away, but then we're going to go back and kind of look at what direction they would be. So just be careful with your sign conventions. Then r times n sine of theta, right? And then we have one more force with a frictional force, r times fs sine of theta. Okay, so what's my radius away for this guy here, for the weight? Well, it's actually acting at the center of mass. So my radius is 0, so this whole piece goes to 0. Okay, what about over here? Well, I do have some distance that the normal force is away from the center of mass, right? Because it's acting on the surface. This normal force is pushing back from the surface. So there is some radius r, but this force is acting through the line for the center of mass. So if I'm looking at the angle it is away, it would be 180 degrees. So I'm going to have r times n sine of 180 degrees. And this also just goes to 0. Okay, because it's unfortunately along the line of the radius. So if it lines up with the radius, you're not going to cause any rotation. Okay, what about this guy? So I have a radius, right? Because this is the radius. This is how far away my friction is away from the center, right? It's acting along this surface, so I'm some radial distance away. Good, okay. F of s, and then what's my angle? Well, if I look at this over here, my force for friction is at a 90-degree angle. Okay, so sine of 90 degrees. Okay, cool. So sine of 90 degrees is equal to 1. Okay. So I will have a torque for that one. So sum of torques. So I have R times Fs just because it becomes 1. So is this positive or negative? Let's kind of think about how it's acting. So if this is my radius or my lever arm here, and I'm pushing, I have my Fs here. Well, the direction that it rotates, that's going to be clockwise. So I'm going to have a negative torque here. Okay, so far so good. All right, so I set up my sum of forces in the x equations, I set up my sum of forces in the y, and I set up my torques. Okay, I also have one more equation, this guy right here, and I know that I can use that because, as we said before, for rolling motion without slipping, the linear acceleration of the center of mass and the angular acceleration are related by this equation. So we have rolling motion without slipping, and the linear acceleration of the center of mass, which is ACM, so ACM is the linear acceleration, right, of the center of mass along a line, is equal to R times the angular acceleration. Okay, so rolling with no slipping, let's use that. So this is our equation number 4. Okay, ACM equals R times alpha. Okay, so now what we really need to do is just sort of simplify all of our equations and see what we can do to rearrange things to solve for ACM. Okay, so let's ask ourselves first, what equations do we have ACM in? Well, ACM is in this first one, right, because it's moving along that x direction. We don't have it here, but we do need this normal force for our frictional force right here. So I'm going to put one more equation in here for 5. We know that f of s max, right, is equal to mu sub s times n. So f of s is equal to mu sub s. I hope I can finish this before it dies. It's equal to mu sub s. And then what are n forces equal to? So this is, I have 0, right? 0 equals n minus mg cosine of theta. So n is equal to big M, mg cosine of theta. So mg cosine of theta. So just subbing in that n. Okay, so I also have an expression for my friction. Okay, so let's sub some things out here. Okay, so let's look at how we're going to approach our algebra. I want to combine. So I know that this torque is equal to I alpha, like we said before. Okay. So let's go ahead and put some stuff together here. So I have negative R times the frictional force, so mu s mg. So I'm taking this torque equation here, 3. Mu s mg cosine of theta, right? This is just, we're just doing number crunching here. And then we're going to set that equal to I, and then my alpha, I'm going to actually relate that to ACM. So ACM over R. Okay, cool. So let's see what else I can do here. I want to find it. Okay, so I have one equation with ACM. Maybe there's a cleaner algebraic way to do this. And then let's look at our f of x equation here, right? I have negative f of s, right, plus mg sine of theta is equal to MACM. Okay, what else can I sub out here? Oh, you know what, actually, so for my final answer, I want ACM, and I have I in my final answer. I subbed in this frictional force, but I'm going to leave that there for right now, like F of S. We're going to just sub out that frictional force. Okay, so let's do F of S is equal to negative I over, so ACM over R squared, and let's sub this into here. Okay, so IACM over R squared plus mg sine of theta is equal to MACM. Okay, cool. So we can combine a lot of things here, right? Okay, so mg sine of theta equals MACM minus IACM over R squared. Okay, let's pull out ACM, right? ACM times M minus I over R squared. Because if I multiply ACM by both of these, like if I distribute it, right, it'll be what it was up there. Okay, so mg sine of theta. Okay, so now I have an easy way to divide. Mg sine of theta over m minus I over r squared, okay, is equal to ACM. Okay, and I think that's in terms of what we were given. Yeah, all right. Oh, I'm sorry. I changed the sign. This is capital M still. There's only one mass in this problem. I should be careful with my capitalizations. I think I just wrote it at some point as a lowercase m, but there's only one mass, so this shouldn't be confusing. Be careful with this. Don't trip yourself up there. Okay. So this is my final expression for the acceleration of the center of mass. I notice this is the same m. Did I have it anywhere else? Oh, I just put them up here. So this is the only one mass. Okay, so to recap what we did for this problem is okay, so we were used to doing sum of forces in the x and y direction, so sum of forces in the x and sum of forces in the y, but we introduced a new concept where we looked at the sum of torques for a rotating object, and to do that we needed to look at the radius, so the distance the force was away from the center, and the angle. So if the force was acting through the center, we found out that the torque was 0. And then if the force was acting through the center, even if it was a distance away, the torque was 0. And then if the force was acting through the center and the distance away was 0, the torque was also 0. So it had to be acting some distance away and not through the center. So it needed to be some distance away and then have some angle where it wasn't pointing through the center for it to have an actual torque. We also talked about how the counterclockwise is for a positive torque. And then we set up our equation here. Oh, and we also found out, we identified the fact that if we have a rolling object without slip, that we can relate the angular acceleration to the linear acceleration of the object. Okay, so we set up our sum of forces in the x, sum of forces in the y, and sum of torques, and then we used this fourth equation here, and then we did some algebra to rearrange, and then solve for ACM. There are multiple ways that you could approach the algebra to do this here. Maybe you can find an easier way. Totally up to you, but essentially all you really need to do here is isolate ACM to solve for the equation in terms of your known variables. Then if you were given a mass moment of inertia for your object, for this rolling sphere, you would plug in the value for your mass moment of inertia. If this was a disk or a sphere, so if this was a disk, you might have 1/2 mr squared. If this is a sphere, you would have a different mass moment of inertia. Please check the table attached. And you could plug that in, and then whatever your rolling object is, you could figure out the acceleration at the center of mass.